I want to talk about neutron star mergers as cosmic factories of heavy elements, and I guess this will be followed up at some later point then by the electromagnetic transients that are the results of that. So I don't have to convince you probably very much that, well, neutron star mergers are wonderful systems to look at because they're related to fundamental physics in terms of gravitational waves here. We can learn from neutron stars quite a lot about nuclear matter properties and maybe actually even about neutron-rich nuclei. They have been suspected for a long time to be the source of gamma ray bursts, and another thing that was speculative for quite a while was whether they produce actually heavy elements or not. And of course this is related, well, first to the enrichment of the cosmos, and of course it has been very nice in predicting these electromagnetic flashes that we think we had seen just last August. So what are we talking about? So we talk about, if you look at the solar system abundances, we talk about these massive nuclei that are formed via neutron capture, and you see you have here this double peak structure, and what that tells us is that nature seems to work essentially in two types of modes, and one is a slow neutron capture mode, and the other one is the rapid neutron capture mode. And these are not just some tiny fractions of exotic elements, we're really talking about something like 50% of the elements that are heavier than iron here. Now, of course, if you slam two neutron stars into each other, that is a terribly complicated process, but there's one quantity that plays a particularly important role for forming heavy elements, and this is the so-called electron fraction, which is just the number of protons divided by the number of nucleons, or electrons per nucleons if you have charge neutrality. Now, if you have a very high YE, and if I say high YE in this context, I mean something close to 0.5, so same number of neutrons and protons. In the valley, you would stay in this type of chart, so where you have the neutron number here and the proton number here, you would stay very close to the valley of beta stability here. Where the nuclear properties are relatively well known. But if you have a very low YE, the actual nucleosynthesis can happen at this border here, which is called the neutron drip line, where the neutrons are so weakly bound that they can essentially drip out of the nuclei. So this is a very different regime where these neutron, very low YE nucleosynthesis cases happen. Now traditionally, there were essentially, well, the front runner for a very long time were core collapse supernovae, and somewhat later neutron star mergers, and they come in a sense from two different sides. In the core collapse case, you start from something that is close to 0.5 and you're deleptonizing to moderate values of YE. While here in the case of a neutron star merger, you start from cold beta equilibrium at very high densities, and it means you start with lots and lots of neutrons, and you can have electron fractions actually, in some cases, substantially below 0.1 to start with. And of course, if you heat up the material, you can reprotonize, and you're approaching the YE from a different side here. Now, if you look at initial neutron star, so cold beta equilibrium for some equation of state and typical mass, then of course you can solve this, solve your Oppenheimer-Volkoff equation. You have a condition that on the chemical potentials, which gives you the electron fraction. And what you find then here as a function of the radius, this is the electron fraction, this is the radius in kilometers, you find something like this. So you're extremely low YE, something like 0.7 or so here, and then the material, or say the YE, rises to in the crust here. But one of the punchlines to take home is that there is actually not much mass in that thing here. And I will discuss it a little bit later. There's something like a critical value for the electron fraction, which is something like 0.25. And especially matter that has an electron fraction higher than this 0.25, this is just a tiny amount in a neutron star, just because the density drops here so very, very rapidly. So you have something like a few times 10 to the minus 5 solar masses in this higher YE material. So that means if you want to understand the nucleosynthesis, you need to know how do you get potentially from these very low YEs to potentially something larger. and that would be mainly by positron captures and by neutrino captures, and that means you need to understand the ejector history of the stuff that is really flying out into space. Now, another point which is simple but still worth stressing, and that was one of the reasons why initially neutron star mergers were not so popular as a nucleosynthesis site, because it wasn't so clear at all whether they eject anything at all, and that is just because gravity is so strong. So if you are a nucleon sitting on the surface of a neutron star, then the gravitational binding energy is of the order of 150 MeV, and that is of course much, much larger than any energy that you could get just from nuclear burning. And therefore it's at least non-trivial to unbind material, but of course if you have another neutron star or a black hole, then of course this may work. Now, I think now we have made a very big progress in last August on this, and just to put this a bit into context, so the origin and the production side of our process elements, that was one of the 11 science questions for the new century, and so it's really has been a very long-standing problem, and there has been seminal work by Burbidge and Cameron in the late 50s, where actually the basic nuclear physics was already understood, but the site was not clear. And of course, at that time, supernovae were the best suggestion that was around, and this only changed then somewhat later. So Jim Latimer, who is also here, had suggested in '74 that you could use decompressed neutron star material, and I think this number is not accidentally the discovery year of the Hulse-Taylor pulsar, and I think motivated by that, they tried to study how much mass you could eject and whether this would be an interesting R process site. And due to technical difficulties, it was easier to do this in a fixed metric with black holes. And it turned out that this could be a potentially very, very interesting site, but it was hard to estimate the amount of mass. And that was something like, well, 5% of a neutron star mass plus minus 5% of a neutron star mass. So it was not clear how much it's really flying out there. Then in '86, there was a paper discussing, well, bringing together the different bits and pieces, discussing neutron star mergers, discussing our process, neutrino bursts, and also suggesting them as sources of GRBs. And then the first calculations on ejecting, how much mass you eject, came then in '98. There we had in May published a conference proceeding from a Ringberg conference that was called, well, Coalescing Neutron Stars, a Solution to the R Process Problem, with a question mark. And it's just 3 pages, and one of the results was, well, it ejects about 1% of a solar mass, and with the estimated rates, this would be enough to explain pretty much the R process that we have in the galaxy. The other thing is we had post-processed some of these trajectories, and we found a very good agreement with the solar system, R process abundances, and in particular this platinum peak that has been a very serious struggle for core collapse supernova models, and here it just came out without any tuning, just the first trajectories showed this, just because the matter is so much more neutron rich. Then this was May. This paper has been studied by Lee and Pyczynski, and they were very quick in August '98, referring to this one here. They just did the next step, and they asked, well, how, if this is true, so what could we expect? And they then discussed for the first time these things that we now call macronovae or kilonovae, and I think at that time they called it mini supernovae. And in the last decade or so, of course, the models have improved quite dramatically, and this has become a little bit of an industry, and just at the right time, of course. Now we have different ejector types. So the first type of ejector that was discussed were things like these. So dynamic ejector, and these I call tidal dynamic ejector because they're just flung out by tidal forces on a very short time scale, just on about a millisecond. That's why they're called dynamical. It's of the order of 1% of the solar mass. And then there's another component which is also dynamic in the sense that it's flying out immediately, but that is coming from interaction of the 2 neutron stars, and this would be more polar material, and since it is heated, it could have a substantially larger electron fraction. Now, there's a second type of ejector. These are neutrino-driven winds, and this is very similar to actually what you have in the context of a protoneutron star. So you have likely a remnant surviving here. You have neutrino luminosities of 10 to the 53 ergs per second, tens of MeV or so as neutrino energies, and this can really drive out matter out of the gravitational potential of the remnant here. So this is typical timescales here, tens or maybe hundreds of milliseconds for this. And then there's a third type, and this is coming from the torus as this evolves, and this is happening on a much longer timescale. This is of the order seconds or so. And this material is unbound by nuclear recombination and by heating, for example, by the MRI, and magnetorotational instability. And this is very interesting because there is a good chance to unbind a large fraction of the initial torus mass. So this could actually be a very important component of the overall ejecta. Now, how do these tidal components look like of these dynamic ejecta? So this is an example of a 1.4 and a 1.5 solar mass neutron star. What you see color-coded is the electron fraction. Chopped off is the upper half above the orbital plane so that you can see inside. And you see in the core you have, well, of the order, something like 10% or so as a proton fraction dropping down to very low values and tiny little fluff of higher YE at the surface. And you see what you eject in these tidal components here is material that is extremely low in electron fraction. So this is something like 4 protons or so per 100 nucleons. And that material is flying out at something like 15% of the speed of light. And typical masses are around, well, 1% or so. And if you really, really want to tweak it with a large mass ratio, maybe you get to 2, 3, maybe 4%, but that would not be the best guess, at least. Now, if you look at the other ejecta type, say these neutrino-driven winds, this is now from a simulation similar to the one that I've just shown, but it's now taken over by a different type of code, which has a more sophisticated neutrino treatment. And if you let this go, so just to guide the eye, the original orbital plane is here. And these are different quantities, density, velocity, electron fraction, and entropy. But maybe focus on the electron fraction here. Then you see you're driving out material in this polar region. And this material, at least according to these simulations, is relatively slow. It's something like 5% of the speed of light. But for the nucleosynthesis, the interesting bit is it has a much broader distribution of electron fractions. There you have something like 20 to 30% or so of protons. And this has a very, very big impact on the resulting nucleosynthesis. And it's very different from these tidal components that I've just discussed before. Now, if you look at the nucleosynthesis, so just 2 examples, this is a trajectory from this very low tidal dynamic ejecta component, and here I'll show after that a trajectory from this neutrino-driven wind. Let's have a look first at the tidal stuff. So here you see all of the nucleosynthesis action initially is happening here at the neutron drip line. Here you see the current abundances. You see you go to this very massive nuclear regime here, and once you are left with radioactivity, everything is decaying back to the value of beta stability. You form a very, very robust pattern with material essentially above 140 as a nucleon number. Now, if you look at the comparative thing for the neutrino-driven winds, you see you're not starting really at the drip line, and you never go to this regime here. And you see the resulting abundances that come out, they're also in a very different regime. So this is still heavy nuclei, but you're not producing these lanthanides and this platinum peak that you form here in this tidal component. Now, if you put these things together, then you just see, well, they work in different regimes here in this neutron-proton plane. The winds are pretty sensitive to the details of the trajectory, but if you take many of them, they add up to something which looks reasonably well close to solar system abundances, while these tidal components here produce especially this heavy stuff and very robustly, and they're not very sensitive to the details of the trajectory that you're looking at. Now, part of the reason why I'm showing this is, of course, this region here, those lanthanides, they have a complicated atomic structure and lots of bound-bound line transitions. and therefore they have a very high opacity, and that has a very big impact on the signal that you would expect. So just to illustrate this a little bit, here you see such a typical R process element compared to the lines of iron that you see here. Okay, now all of you probably know very much about the system that has been observed. So really last August, the multi-messenger era finally has begun. And one of the very exciting things was, of course, that there was an electromagnetic transient observed apart from the gravitational waves. And it evolved from an initially blue signal to a red signal later on. Now, one of the questions, of course, the people that have worked on this would have expected that you would form R process and that this would produce this signal. But of course, the question is this really true? And just to illustrate the point a little bit and also this critical value of 0.25, I'll show you a little experiment. So this is, I take a spherically symmetric cloud that expands at 25% of the speed of light. And what I'm varying is the electron fraction. Now, this is this 5%, so typical for the tidal dynamic ejector, and you see you form the heavy part just as described before, and you see it hardly changes up to maybe 0.15 or so. But even at 0.20, you still have this platinum peak here, but at 25, it really breaks down, and you don't produce these lanthanides in the platinum region anymore, and you still produce some R process, but in this lighter regime here. And nickel actually only, you produce this only at electron fractions close to 0.5, because that was also discussed at some point as a potential electromagnetic transient source. Now, this is now a somewhat extended such experiment. There I'm taking again such a matter distribution and vary velocity and electron fraction, and I'm looking at the nuclear heating rates that I get out of that. And I'm overplotting here the observed bolometric luminosity in those yellow dots. And what you see as the different lines and the different colors are the heating rates scaled with some mass and compared with this observed bolometric luminosity. And what you see here is you have a very nice fit with the slope of that bolometric luminosity, provided that the electron fraction is very low, something like 0.3. Or lower, and that really tells us, well, this is really our process. And if you increase the electron fraction, you get something very different. For example, if you look at this idea of the nickel wind, this would produce a completely different slope here. Now, you may have seen, well, I've cheated a little bit. One thing is a heating rate, so that's energy per time and mass. The other thing is just the luminosity, so there's a mass missing. And I have scaled this stuff here with 1.5% of a solar mass, and of course the interpretation is if all of the radioactively produced energy, really 100%, would go into the observed luminosities, then you would need at least 1.5% of a solar mass. And that means in practice you will have multiples of this robust lower limit here that has been probably ejected. Maybe another thing, one of the questions was, are there lanthanides involved or not? Just based on this type of slope, you cannot decide. Some of those trajectories do contain them, others do not. So the limiting thing is just this 0.3 here. Now, how do we think this may have looked? So this is a sketch where we have the remnant here. So the first stuff that would fly out are the dynamic ejector in this direction, potentially shock-heated material, so the polar component here, and this very low YE tidal dynamic ejector. They fly out first. The next thing that is then happening is, on a somewhat longer time scale, are these neutrino-driven winds. Again, in the polar region, they have higher YE, are therefore expected to be bluer, and get a bit redder towards the orbital plane. And last but not least, you have this secular type of ejector, this unbinding accretion torus, and that is pretty, this seems to be pretty isotropic and has a broad range of YEs. I think at the moment the existing models point to relatively low YE material and the red component, but I think there's much more to study here. Now, if you look at all kind of models, different groups have looked at this, trying to get numbers out of that, and they don't agree on the details, but the ballpark numbers are pretty much the same. And one of the interesting things is the blue component actually contains something like, well, 2% of a solar mass at a relatively large velocity. And the red component is an even larger mass at, well, those expected typical tidal ejector velocities. Now, what are the implications of that? So one of the implications is just this red component. It's not impossible to get this just by the tidal component, but it's for sure not the best guess. This number is very large, and really you need to twist your models quite a bit to get out 4% of a solar mass in this component. So that may mean, well, there may be additional ejection mechanisms. One is this disk ejector, and as I'd mentioned before, that is potentially a very large mass reservoir, but at least according to the calculations that I'm aware of, the velocities would be substantially lower than the velocities that have actually been observed. And I guess right now the current models say, well, likely the bulk of that is below this critical value, but I think there's probably still a lot of room to be explored here, and maybe there's also a blue component coming out of that. But that also tells us something about what physics is really relevant for modeling these things, and one of them is, of course, the nuclear recombination in that disk and really resolving what the magnetic fields are doing. And it's particularly important to stress really like weak interactions and neutrino transport are really fields that need to be focused on for the future modeling here. Now about this blue component, this was, to some at least, quite a surprise that there's so much mass in that. And just to remind you, keep in mind this original profile of the neutron star. That is just a tiny fraction that is above this 0.25. So that was just a few times 10 to the minus 5 solar masses. And now we are there at, a couple of percent. And that means weak interactions and neutrino physics have really played a key role in raising the electron fraction in a huge chunk of the ejected material here. Now just to illustrate this, that is neutrino absorption. So this is from a recent paper by Perigo and Radice et al. And they look at ejector for this particular system, and they run the simulation once including neutrino absorption and once without. And you see the neutrino absorption is really what lifts a lot of the material above this critical value of these 0.25 here. So, and again, that stresses that, well, maybe we need to move towards the direction that people in Core Collapse have explored already a while ago. We really need to get to an accurate neutrino treatment to really know, is matter just below this critical value or just above this critical value? Now, the likely merger outcome is that you have a stable neutron star, at least stable for some time, and this could, of course, help increasing this blue component. But again, the things that likely influence the evolution and the lifetime of that thing are topics that are actually pretty difficult to model: turbulent viscosity with magnetic fields and neutrino transport. And as I said, this is really stuff one should focus on for future simulations. Another thing that was somewhat surprising is that, at least if you have taken the models that came out before the observed event, the velocities were typically something like 5% of a solar mass, and therefore substantially lower than what has been observed. And now, of course, one could say, well, maybe there are other ingredients like strong magnetic fields and a very rapidly rotating neutron star that wants to blow out a neutrino-driven wind anyway. Another thing is, of course, if you want to launch a jet, that potentially has to go out through the material that has been launched earlier on. And this could, of course, redistribute and mix different of those components that we've just talked about as, well, kind of isolated components right now. Now, further challenges for the modeling are, of course, the scales. So if you keep in mind, if you want to do a numerical simulation there, you're solving a partial differential equation. You're constrained by stability by the so-called Coulomb-Friedrich-Levy criterion. And that tells you that the signal speed in your matter sets the numerical time step that you can take. And since in a neutron star the signal speed is very close to the speed of light, or at least a very good fraction of it, that means typical numerical time steps are of the order 10 to the minus 6 seconds or so. But the peak time scales are something like 10 to the 5 seconds. So you have really a big problem if you want to do this at least in one global simulation. I guess this is close to impossible. And now, another thing to keep in mind is the other involved scales. So this is, we tried to follow, a couple of years ago, we tried to follow what would the ejected material do on a longer time scale, and there we just put together, in a sense, two simulations. The second one just focused on the expanding material. And there we were following in total, we were following this up to 100 years after the merger, and keep in mind a typical hydro simulation of the mergers of the order of 30 milliseconds or something like that. And you see the first week or so, the density is dropping by 30 orders of magnitude, and that of course also puts a lot of challenges on just even the equation of state that you want to use over those 30 orders of magnitude. And so the scale is another thing, and I think we at the moment we have only relatively vague ideas about how the remnant looks on large scales at the time scales that are relevant for the peak emission. Now, to summarize, I think we have a very strong case that it's really our process powering this. One thing that came as a bit as a surprise is the involved masses are very large, somewhat dependent on the model that you put in, but I think we have very strong evidence that it's at least a few percent, and that may mean maybe there are other ejection channels or they work differently than we think, and maybe magnetic fields help a little bit there. But one thing for interpreting the observational results, I think it's really clear that probably we need winds and the secular ejecta, and this is of course stuff that is very difficult to model. Just this one event has also stressed, well, that we have to actually do these type of things, and that stresses, well, the need for accurate neutrino treatment. And I guess most of us agree, or probably all of us agree, maybe this was a pretty particular event. The ejecta mass are very large, and also the estimated rates from that event, from that one event, are also at the high end. So we want to know, of course, how particular was this, but hopefully very soon we'll know more about this. Thanks a lot.
Thank you. Very nice. Questions? Brian?
I guess it was just a comment. One other thing against making the large ejecta mass be a tidal tail is also the inferred velocity. I guess it seems, usually in the dynamical ejecta we see velocities of 0.2 or 0.3 c, whereas the bulk of the material was inferred to be a bit lower for this event. And then my other comment is, it's true for the disk winds, we were originally finding about 0.05 c for the average velocity, but we weren't including the additional enthalpy PDV work, and when we add that in, we get up to about 0.1 c. So it seems like the velocity matches pretty well as well.
But some of these models claim that you need something like 25% of the speed of light for the.
Well, for the bluer component, but for the bulk.
Okay.
Yeah.
Yes, Smara.
Do you expect that the spins and their orientation will change your story here from the mass and the ejection mass and the baryon and the electron fraction, the velocities, and basically the entire story?
Not dramatically, I would think. We had explored this a long time ago, and a couple of people have, and you need very, very large spins to make a substantial change to the matter distribution there, and the main reason is just you have this gigantic reservoir of orbital angular momentum, and you need a sub-millisecond neutron star to make a very big difference to that.
Well, we'll go in order here. Vicky, moving down the row.
Stephan, for the dynamical ejecta, the mass has been connected to mass ratio in the binary. How about the disk ejecta, and particularly the disk wind masses? In black hole neutron stars, the connection has been made to mass ratios. I'm wondering about neutron stars, whether you think we can make that connection, whether it makes sense physically or not.
I think the connection is there, just kind of like doing the inverse problem in a unique way is probably very difficult. But I think it would help in all kind of things. Say, if I really twist the mass ratio, if I take something like, I don't know, 1.8 solar masses with 1.2, I could probably get to close to 0.4%, close to 4% of the ejector mass. Question is this likely to happen? So I'm not saying it's impossible, but the mass ratio for sure helps for this component, but also the disk mass is also relatively sensitive to the mass ratio. So if you have a deviation from that, you expect a large initial disk mass, and if these first studies give us the right numbers with 30 or 40% actually of the thing being unbound, then of course the mass ratio would also help for this secular.
For a higher mass,
Yeah.
yeah, thanks.
Fred?
It's a quick follow-up.
Yeah.
I don't understand. If the mass ratio is extreme, one star basically disrupts the other. You don't get the kind of more equal head-on collision that you need to get a lot of these hydrogen.
Well,
What am I
it
missing?
depends. It may change also the relation between those. Well, I call both of them dynamic ejector, but one is this interaction component, and this is the one that is probably enhanced if you have this well, by a softer equation of state and by this more head-on collision. And the other thing is this tidal component. And then with a mass ratio deviating substantially from unity, of course, this tidal component gets substantially enhanced, and you would expect more radar stuff to see.
Quick final questions? Anybody?
Yeah.
Yeah.
So I liked your calculation of just taking the bolometric luminosity and putting a lower bound on the mass, because I think it's a very straightforward way to do it. But it does sweep a lot of information under the rug about the composition of the material, because you're not looking at the relative distribution of light across the spectrum. And I think if you actually look at the change in color as a function of time, as well as at the actual spectra, those do seem to suggest that there is some fairly appreciable fraction of the mass in lanthanide-rich, 1% of the mass or something like that in lanthanides.
No, so I just wanted to be agnostic and say, can we learn something from this decay curve? And I don't think we can. We just know it's below 0.3, and with 0.3 you can have either the platinum peak or you cannot have it. But that's just part of the reason why I showed this initial neutron star. You just have a tiny, tiny fraction of material above this 0.25. So, and I would find it very, very unnatural if you lift all the ejector above this. So it's the best guess is, of course, you have these lanthanides in there just because you cannot raise all of the ejector above the limit. I perfectly agree with this. I just wanted to know, can we say something about this just from this bolometric light curve? And I don't think we can.
Just a quick...
Very brief.
Very quick. Is it, for such a large ejector mass, is it possible to say something from the gravitational wave signal? Would it affect in any way something that LIGO?
I don't think LIGO would have any chance to see that. No,
well, it's more than 4%, he said.
Yeah, but nevertheless, it's 4% at torus-like expanding or so. I don't think you would see very much of that.
Okay, well, we'll wait for the next one to answer that question, right? So thank you again, Stephan. Thank you, Stephen.